Bonjour tout le monde. Donc, bienvenue au séminaire Uranus. Donc, Alexis a un bac en sciences de la météo de l'Institut des hautes technologies des sciences appliquées de la Havane, à Cuba. Il a travaillé comme spécialiste en météorologie au Centre de physique atmosphérique de l'Institut national de météo à Cuba pour quelques années. Il a fait une maîtrise en sciences de l'eau à l'INRS, donc l'Institut national de recherche scientifique au Centre Eau-Terre-Environnement à Québec. Et il est présentement en train de compléter un doctorat, encore une fois à l'INRS, en collaboration avec Uranus. Son doctorat est sous la supervision de M. Alain Maillot. Alexis va faire sa présentation en anglais. Les questions pourront être posées en anglais ou en français à votre préférence.
Okay, the title of the presentation is the response of daily and subdaily extreme precipitations to change in surface and dew point temperature. My name is Alexis Perrez-Bello. I'm a PhD student at the Institut National de Recherche Scientifique under the supervision of Alain Maillot from the Institut National de Recherche Scientifique and Dominique Pacan from the Uranus. Flooding, landslides, soil erosion, crop damage, and degradation of water quality are just few examples of how extreme precipitation events may affect ecosystem, the economy, and human activities in general. These events have become more frequent and intense over many regions of the world, for example, in North America and Europe, and are expected to become even more frequent and intense in the future as climate warms. The relationship between extreme precipitation and surface temperature has been studied to assess how extreme precipitation may change under warming conditions. This kind of relationship will help us to understand what are the main processes involved in the change in the extreme precipitation. And given that the future projection on temperature are considered to be more reliable than those for extreme precipitation, this relationship, the temperature precipitation relationship, was analyzed in order to obtain more robust extreme precipitation projections. The basic idea is that the warmer atmosphere can hold more moisture and therefore trigger more intense precipitation. So once we increase the temperature, the atmospheric moisture holding capacity also increase, and it can be described by the Clausius-Clapeyron equation with the rate of increase of around 7% by Celsius degree. Under some assumptions, like for example, the relative humidity will remain constant in the future climate, like extreme precipitation events are mainly determined by the water already in the atmosphere, and that in the future, not significant change in atmospheric circulation are expected. So it is expected that change in extreme precipitation intensities should follow the rate of change of the atmospheric water holding capacity with temperature as defined by the CC equation. How has been studied this temperature precipitation relationship? A different statistical approach had been used to investigate the temperature precipitation relationship, and the most common one being the binning approach or binning technique. According to this approach, rainfall records are partitioned into temperature bins. And the precipitation intensity corresponding to specific percentiles within each bin are estimated. So we have the rainfall events and the corresponding temperature, let's say the daily value when these events occur. And we define a bin, a range of temperature, let's say 1 degree or 2 degrees, etc. And all the grid points, from all the grid points that are there, we estimate the percentile, and we do this for all the range of temperature until we obtain a relationship. And the slope or rate of change of this rainfall intensity events with temperature is defined here as the temperature precipitation scaling rate. And as was mentioned before, it should follow the rate of change of 7% by Celsius degree. However, the response of extreme rainfall events to temperature change can be affected by many factors. For example, the geographical region, and here, for example, I just present a work carried out by Oksumi in 2011 when they used 8,900 stations distributed in 0.5 degree by 0.5 degree grid box around the globe. And they found that this relationship was a monotone increasing relationship for the northern region. So once we increase the temperature, the rainfall intensity will increase. They also found monotone decrease relationship in the tropical region and monotone increase relationship at low values of temperature and monotone decrease relationship at high values of temperature. And this behavior of decreasing of the rainfall intensity with temperature can be also associated to a key factor in the extreme precipitation generation process, which is the atmospheric moisture availability. And in fact, Lendering and Meyer in 2010 proposed to use dew point temperature instead of surface temperature to account for the available moisture in the atmosphere, eliminating by this the assumption that relative humidity will remain unchanged with temperature in the future climate. Zhang, 2017, proposed another way to estimate this relationship, the temperature precipitation scaling rate. And basically, they proposed to use the summer maximum precipitation with the summer temperature, for example, the average value of the summer. And they combined this information by fitting a distribution, a GFD distribution, a generalized extreme value distribution, using the summer temperature as a covariate. It's a non-stationary fitting. And the scaling was defined by these authors as the rate of change of return levels. For example, the 50 percentile with the temperature. It was how they defined the rate of the scaling. The work that I'm presenting here was already published in the Journal of Geophysical Research, Atmosphere, and the main idea, the two questions that we have, first one was how daily and subdaily extreme precipitation responds to change in surface air temperature and surface dew point temperature over the Northeastern North America. And the second question was can we use the scaling rate in the historical period to estimate future change in precipitation extremes? To do that, we use the Canadian Regional Climate Model Large Ensemble, which has a 50 member, is defined here with this red line, the domain. We focus the analysis only in land grid points. We exclude the ocean. This Canadian Regional Climate Model Ensemble is a dynamic downscale version of the 50 members Canadian Air System Model version 2 large ensemble. They use observed greenhouse gases emission up to the year 2005 and forcing a scenario RCP 8.5 from 2006 to 2099. It also has a spatial resolution of 0.11 degree, which is around 12 kilometers. And the study period goes from 1956 to 2099. From the Canadian Regional Climate Model Large Ensemble, what we use 1 hour total precipitation because the total precipitation was available at 1 hour. We use a 3 hour surface air temperature. We use a 3 hour surface relative humidity. We estimate surface dew point temperature. The 3 hour series were estimated from surface relative humidity and surface air temperature. And 2 75 years periods were defined. One going from 1956 to 2030, and the other one from 2025 to 2099. The first one was called like a historical current climate, and the other one was called like a future climate. The scaling estimation here was based in the approach proposed by Zhang 2017, and here we use the May to September maximum precipitation at different durations. So from 1 hour to 24 hours, we use the May to September average temperature, and we use for surface air temperature and for surface dew point temperature. We fit the distribution by using this average temperature for both covariates. We use it as a covariate in the scaling estimation. And the temperature precipitation scaling rate for each member, for the 50 members, was defined as the rate of change of return levels with temperature. And we use different return levels here, going from the 50 or 2-year event to until 99 or 100-year event. The uncertainty of how robust are these scaling estimation, to do that, we use the index proposed by Lee in 2018 that is called the scaling rate per standard error, which is basically the ratio between the best estimate of the scaling rate divided by the standard error. The best estimate of the scaling rate, as was mentioned before, we estimate the scaling rate for each member independently, and the best estimate is the ensemble mean. And the standard error is just the standard deviation of these 50 members scaled by 1 over the square the number of members. So based on this index, there are 3 categories that were defined by these authors. The first one was unconstrainable, so at low values of the scaling rate per standard error, so it shows that the natural variability prevents the detection of any robust response of extreme precipitation to temperature change. So we have a higher standard error compared with the estimation, with the best estimate for the scaling rate. Constrainable is when a response is detectable, but the magnitude is relatively uncertain. And the robustly constrained, so it's when the significant response of extreme precipitation to temperature can be detected through the scaling rate. And this is what we really wanted to see, robustly constrained estimation, etc. Here, I just show you some of the results that we obtained. And this figure displays the map of the grid point, the temperature precipitation scaling rate values for the 1 hour 99 percentile precipitation over the domain for the historical period, and when we use a surface air temperature as a covariate. So we can see here that the scaling values are positive for the northern part, but for the southern regions, negative values are observed. However, when we use a surface dew point temperature as a covariate in the scaling, in the temperature precipitation scaling rate estimation, we can see that we found a strictly positive and higher scaling values over the entire domain compared with the surface air temperature. And in the future, here, these are the change in the temperature precipitation scaling rate, just essentially the scaling in the future minus the scaling in the historical period. So we can see large increase in future scaling values are observed for surface air temperature here in the southwest part of the domain. And when we look at the change for surface dew point temperature, we can see that they are smaller and randomly distributed over the entire domain. This figure now here shows the corresponding longitudinal distribution for the 1 hour scaling for SAT and surface dew point temperature that we saw in the image before, in the historical and future period for the 99 percentile precipitation. The diagram here in the right shows how this longitudinal distribution were created. So here we took a latitude range represented here by the black segment, and all the grid points that are inside this latitude range were used to estimate the distribution values like the median and the 5 and 95 percentile interval. This latitude range or bin, let's say, was moved from north to south to build this longitudinal distribution that we can see here for surface air temperature and surface dew point temperature. In this longitudinal distribution, the solid line, blue and red, represents the median value of this, and the shaded regions represent the 5 and 95 percentile intervals. The vertical black line corresponds to 0, and the dashed black line here corresponds to the CC relationship, or 7% per Celsius degree. And latitude beams here, latitude beam, or this black segment, are 1 degree wider and are overlapping over 0.5 degree. This image, this longitudinal distribution that we have here in the historical, the left, and for the future in the right, shows that the difference between the temperature precipitation scaling rate using surface air temperature and surface dew point temperature increase. This difference increase when we move from north to southern regions. Basically, the surface dew point temperature change moving southward goes from values close to the CC and above the CC, while surface air temperature scaling comes with value below the CC and can go also even negative for the southern part of the domain. It shows that the available humidity is a limiting factor in the southern part of the domain and can even result in negative scaling when surface air temperature is considered. So these results support previous report conclusion that the surface dew point temperature covariate to assess possible change in subdaily extreme precipitation is better than when we use a surface air temperature, previous studies. Also, it shows that the negative scaling rates in the southern part of the domain are related to moisture availability and atmospheric circulation, limiting the transport of moisture in these regions. Here, I show now the percentage of land grid points with robustly constrained temperature precipitation scaling rate as a function of different duration for both periods and for percentile from the 50 and 99 percentile for surface air temperature in the left and for surface dew point temperature in the right. So we can see here that the fraction of robustly constrained scaling presents values close to 100 for surface dew point temperature, but much smaller for surface air temperature. So values close to 100 here for surface dew point temperature and much smaller for surface air temperature. Also, it decreased in both cases as duration increase, and it is also larger for the future period compared to the historical period. So these results indicate that the link between extreme precipitation and temperature change is stronger for short duration precipitation events and for the future periods where the signal to noise ratio is larger. This link is also stronger when surface dew point temperature is used as a covariate compared with when you use a surface air temperature. So therefore, hereafter, we will just present results based only on surface dew point temperature. This figure presents the distribution over of the scaling values over the entire domain for the 99 percentile precipitation as a function of durations. Here, the dash line, black dash line, represents the CC scaling, so around 7% by Celsius degree. And we can see that the scaling here is higher for shorter duration events compared with the longer duration event, and no significant change are observed between the historical period and the future. And it shows that, basically shows that the shorter events will be more impacted by climate change, which is a result already reported also in previous studies. And we can see that for 1 hour, values can go above the CC. The majority of the values can go above the CC scaling, and for 24 hours can slightly go below the CC scaling. Regarding the difference in percentile, so the dependence of the scaling on precipitation percentiles was also analyzed here by taking the difference between the scaling values of various precipitation percentiles and the corresponding 50 percentiles, so at each grid point. So here we estimate the scaling for the 99 percentile, the 50 percentile, and we just make the difference. So the 99 minus the 50 percentile. And we can see that the domain is divided in two. This is just one example, just to show you that, for example, when we compare the 99 with the 50 percentile scaling, the domain is divided in two. So the northern part with positive change, and the coastal region also in the southern part of the domain displaying positive change between the 99 and 50 percentile. That so it suggests that increasing the scaling rate on coastal areas for more extreme precipitation. And the hypothesis that we have for this behavior is that the region here displaying positive change in this figure corresponds to regions where moisture availability enables an increase in extreme precipitation events of different intensity. This is the, and however, for regions that are negative change corresponds with the regions where atmospheric circulation weakens or reduces the thermodynamic response. This is a result that has to be further investigated. We also take a look at the difference of the scaling between the historical and the future, just to see if the scaling that we estimate in the historical period can be used to make projection about precipitation change in the future. And this figure shows the maps of the land grid points with significant and not significant change, which is at 95% confidence level. So of the 1 hour total, 1 hour precipitation, and for the 50 and the 99 percentile here. It shows that the scaling values here for the 99 are near the percentage of grid points that present no significant change between both periods are close to 87%, compared with for the 50 percentile that are close to 63%. So we can say here that despite the scaling is different from the CCS scaling, because we saw that for 1 hour can go above the CC, etc. The results show consistent scaling based on local seasonal surface dew point temperature anomalies between the historical period and the future period over a large part of the domain. So here for the 99 percentile, 87% of grid point percent, no significant change. So to finalize, here we have some key points just to answer the question that we proposed at the beginning: how daily and subdaily extreme precipitation responds to change in surface air temperature and surface dew point temperature over the Northeastern North America. So we can say that the scaling temperature precipitation and scaling rates were close or slightly smaller than the CC scaling in the northern region. We also see contrasting response for surface air temperature and surface dew point temperature when we move from north to southern region, and essentially the scaling based on surface dew point temperature increased to reach a super CC, while the scaling based on surface air temperature decreases and display negative values. Also, the scaling using surface dew point temperature provides more robust estimate compared to the scaling when using surface air temperature. The link between extreme precipitations and surface dew point temperature change is more robustly constrained for short duration events and for the future periods. And also, to answer the second question, can we use the scaling rates in the historical period to estimate future change in precipitation extremes? And the answer is yes. The scaling by using surface dew point temperature in the historical period can be used to estimate change in rainfall extreme in the future over most of the Northeastern North America region. Future work that we plan to do now, we want to estimate also this relationship between temperature and precipitation from an event-based perspective, instead of using just the annual maximum here that we use. Annual maximum is just a part of the event. So we want to use the event-based perspective by using the convective dominant events and stratiform dominant events, etc. And also try to identify the conditions that could explain the super CC in the southern part of the domain. So thank you so much.
Merci, Alexis. Est-ce que vous avez des questions? Je vois une question de Philippe Lucapché. Vas-y, Philippe, tu peux ouvrir ton micro et la poser directement.
Okay. Bonjour, Alexis. Hi, Alexis. Thanks for your presentation. Very interesting. Very nice way to present the results. I was wondering about the period that you chose for your study. I mean, you use 75 periods like in the past, 75 years in the future. I find those periods very long, and so because within 75 years, you will find very different precipitation. And I wonder why you didn't choose like the classic 30 years period, like maybe a short range, medium range, long range.
Okay. Here we just define the 75-year periods because we use for the estimation of the scaling, we use we fit the distribution there, and by using the annual maximum, and we try to extend the longest the period. Here it was 75 years because to better estimate the GFV parameters, the generalized extreme value parameters, we also did a pooling strategies to do that, because I didn't mention, but we have to pool grid points close to the main grid point, etc. And that's why we use a 75-year. We basically divide the period in two by just, if you look closely, you will see that there is a 6-year overlapping between both periods. And the idea was to just see, okay, one in the historical and one in the future. And the idea was to extend longest period to give us the possibility to estimate very extreme events like 99 percentile, etc. So with only 30 values would be.
But
okay.
But you still have 50 members. I mean, you still have a large ensemble, a large sample. Do you really need to take 75 years, despite that you've had 50 years of all those summers?
Yes, but here the members were treated independently. So
okay.
we estimate the scaling for each member independently.
Okay.
Then we estimate the ensemble mean, and the ensemble mean was considered as the best estimation. You know, that's why. Okay. That's why we have to do like that, 75 year. There is another way, is combining the 50 members, but by combining the 50 members, the results will be quite similar, I think. But we use each member independently in order to see how natural variability making influence, you know, to see how the scaling is robustly constrained or not, etc. So that's why we use like that, 75 years for each member. And also we use a pooling strategy for each grid point. We use the 9 neighbor points.
Thank you.
That's why.
Okay. Okay, thank you.
Est-ce qu'il y a d'autres questions pour Alexis? Oui, Alain Maillot. Tu peux y aller, Alain.
Oui, en fait, juste pour compléter la réponse à Alexis, pourquoi on prenait 75 ans, il faut comprendre que nous, on s'intéresse à une relation entre deux variables. Donc, cette relation-là, pour qu'elle se manifeste, donc on fait une relation entre les précipitations extrêmes et la température, on a besoin d'une période relativement longue parce qu'on construit sur cette relation-là. Alexis l'a un peu expliqué, là. Et effectivement, chaque membre était traité indépendamment. Donc, on n'a pas certes, 50 membres, c'est intéressant parce que ça nous permet de voir l'impact de la variabilité interne, mais on a besoin de considérer une relativement longue période, justement parce qu'on a une série de températures estivales, d'anomalies de température estivale qu'on essaie de corréler à des précipitations extrêmes, deux séries en parallèle. Donc, il nous faut une 30 ans. Bon, je ne me souviens plus si Alexis l'avait essayé, mais clairement, puis on montre aussi, c'est ça le résultat, je pense, le plus intéressant de l'étude, c'est qu'on montre que cette relation-là elle est la même qu'on conçoit en climat passé au futur. C'est comme une constante. On aime ça en physique, des choses qui ne changent pas, là. Donc, c'est comme une constante. Donc, on est capable de prendre une des variables puis en climat passé, puis de projeter ce qu'il y a en climat futur. Donc, c'est un peu pour ça qu'on a considéré 75 ans, mais certes, ça demeure un choix dans une certaine mesure arbitraire.
Merci pour les précisions, Alain. Philippe, est-ce que tu viens de relever ta main ou…
Oui, c'est une nouvelle main.
OK, c'est beau. Tu peux y aller.
J'en profite vu qu'il n'y a pas d'autres questions.
Oui, vas-y.
Thanks, Alain, for the clarification. And so this give a good reason why you choose this method, and you chose this method. And I have another question. I've seen this scaling rate many times, and I was always concerned or wondering something. And so when the precipitation, let's say the 99 percentile precipitation occur, okay, say at 6 o'clock in the afternoon, do you take the temperature at the 6 o'clock in the afternoon before or after? Or, I mean, because if you take it, I mean, during the same hour, sometimes the temperature will drop because of the rain that falls and all those details. And I was always having in mind, okay, what temperature was taken for that study, and I think this is a big concern. I mean, it may change a lot depending what temperature you take the day before, the hour before, the hour after, the same hour. I mean, I will let you.
Exactly. If you look at the literature, it changed. There are many ways to do this. Many people use the average value, the daily value, in that day when the extreme event or when the precipitation events occurs. And also some people use 4 hours before, 2 hours, or 12 hours before, etc. But here we use the May to September average value. We didn't take a look at the hours before or something like that. We just take a look at the average value over the May to September period. So it's just the average value. And I think that it's better to do like that instead of using the hours before or something like that. That's why we use the general value from May to September.
I understand the idea, but this, I mean, by making a long mean or over a long period, I mean, this dilute the event. I mean, we pay attention to specific precipitation extremes, okay, that occur on a specific day or over specific conditions, okay, but then you take a mean over a full summer. This is far from the moment that the precipitation extreme occurred. I mean, and I understand the reason. I mean, but still,
other people also use the mean over the year. You know, we were focused on May to September. And when you look at the literature, other people also use the mean over the year, because the idea is to see the general change in temperature, not some local temperature that change from day to day. You know, when you take day-to-day variation, it also is also influenced by the seasonal change. You know, when you take the day-to-day variation, the seasons making influence also.
But the assumption behind this hypothesis is that that the warming is constant for all the days, for all the situation, but I'm not sure this is the case. But okay, so thanks for your answer. I will let the chance to other people to ask questions.
Okay.
Je ne sais pas si Alain, tu voulais répondre à ça peut-être avant de laisser Olivier poser sa question. Oui, ok, vas-y.
Je voulais juste ajouter quelque chose. Je comprends tout à fait les questionnements de Philippe qui viennent d'un physicien. Le traitement ici, et je dois l'avouer, c'est une chose que je n'aime pas trop dire souvent, là, mais le traitement ici est statistique. C'est-à-dire qu'on se dit qu'on ne regarde pas l'extrême et la température associée. Il y en a qui l'ont fait, là, on peut montrer que le scaling existe, mais nous, on regarde plus, il y a un événement extrême qui arrive un été, comment cet extrême-là est associé de façon globale à l'anomalie de température de cet été-là. C'est à l'échelle de la saison. Juste pour dire qu'il y a d'autres études où ils regardent l'anomalie de température. Nous, on a regardé au point de grille. Eux, ils regardaient à l'anomalie de température mondiale. Donc, tu vois, encore là, l'échelle est encore plus grande. Donc, l'idée, c'est ça, c'est de voir en moyenne ou d'un point de vue statistique comment une anomalie de température sur une saison peut être favorable à générer des extrêmes plus importants. Puis on voit que c'est quand même intéressant parce qu'on voit qu'il existe ce scaling-là, on a montré qu'il est robuste et c'est une variable que les modèles, on pense, ne sont pas si mal pour simuler. La température moyenne sur une saison, on pense que c'est bon. Donc, on est capable d'associer ces évolutions de ces températures moyennes-là avec les précipitations extrêmes et il semble que le lien entre les deux, qui ne doit pas être vu comme un lien événementiel, mais un lien statistique, bien, il y a un lien. C'est-à-dire que l'atmosphère se réchauffe, c'est plus propice à créer des événements plus extrêmes, puis c'est ce lien-là qu'on a investigué. Puis on n'est pas les seuls, hein. Il y a la littérature là-dessus, il y en a des tonnes. Là.
Okay, merci
voilà.
beaucoup. Merci beaucoup pour les clarifications. Okay.
Merci Alain. Olivier, tu peux y aller.
Well, thanks, Alexis. That was a very nice presentation, also very accessible for non-experts. So I have a non-expert question. You showed different scalings for different regions of the globe. I think it was from another paper. And so from what I understand, the kind of high latitudes where you were like kind of Quebec region, there's no moisture constraints. So you see like the Clausius-Clapeyron scaling. And then when you got lower, then I guess there was more moisture constraint around like 30 degrees. But what about the tropics? Is it similar to, say, Quebec? Like, do you also see a CC relation? Because you did show a curve that was going in the other direction. So I was wondering, is this from air temperature or dew point, or?
It was the decrease in the southern in the tropical region. They observed a decreasing relationship, and it was mostly related with the moisture availability limitations and also with the duration of the wet events, etc. They explained that in that work. That was most.
And was it the curve you showed? Was it from SAT or was it from with the dew point?
With the surface air temperature? Yes, I think it's a generic curve that I showed. It's just to show the different patterns around the globe, and just to see that it changed. It changed different depending on the region, etc. And that's it. It shows the decrease in the trend in the tropical region.
So even if it's not. I was assuming that in the tropics you would not have moisture constraints as you would like in the more desertic regions around 30 degrees. But so
but when in the warming condition they show that it decreased, and it can be probably mainly because of the binning technique, because it was based in the binning approach technique, which is a technique that now was widely criticized. Now most of the people criticize that technique because the extreme precipitation that you estimate there are not the annual maximum, etc. And it can happen as mentioned in the other question. When you have an extreme event, it can cools the temperature and it can move to the lower binning, producing a negative scaling. So it can be also due to the scaling approach estimation. So.
Thank you.
Peut-être une dernière question par Monsieur Guy Féliot.
Oui, bonjour tout le monde. Thanks, Alex. A very interesting presentation. I'm not a climatologist. I'm not a climate scientist. I take your information and I apply in climate risk assessments. So very informative. It's a two-part question. One, and I know that it wasn't really the scope of your study, but I'd like to get your impression. One is you stopped at the short duration events, 24 hours. And in some cases, what we are also concerned about are the 3 to 5 day precipitation events. So, any indication that your relationships would apply to those longer term events, although you showed very clearly that when you get into the 24-hour events, then the scaling is not as robust. And the second part of the question is related to when you chose May to September. But in many cases, what is causing some of the more intense flooding in Eastern Canada is the late spring or late winter, early spring precipitation events. So we're talking about March and April. Any indications that your relationships would also apply or to those kind of events? Thank you.
Okay. Okay, I will answer the second first. we take from May to September because we wanted to use like a period over the year that can be like a most applicable over the domain, because as we can see, the domain is quite high. And we take, for example, from March in the northern region can be some events that could be due to snow, etc., and that could be a little bit more complicated here and to analyze. And also here we focus from 1 hour to 24 hours. So once we increase the duration, this relationship becomes lower. So it decreases. So it's this relationship, and it's for the high, for the most extreme, for the hourly values, etc., is it's better applicable. And also we can see that for hourly values, this relationship can go up to the CC or even 2 times the CC, or 14% of increase in the events per Celsius degree. So that's it. So we use for 1 hour to 24. I think that for longer duration, the scaling will be lower, because in longer duration, we include also periods without rain, and it will make an influence in the scaling estimation. I don't know if it answers your question, or I don't know.
Alain, si tu veux compléter, même si M. Filliot a l'air satisfait de la réponse. Là, mais...
Non, les questions de Guy sont excellentes, là. En fait, la relation qu'on établit entre la température et les précipitations extrêmes, elle est basée sur la relation de Clausius qui est valable pour les événements qu'on dit convectifs. Donc, les événements qui sont plus des orages, des événements de courte durée, des événements plus intenses de courte durée. Quand on considère des extrêmes de plus longue durée, bon, on voit que la relation devient moins évidente. Puis quand on va vers 3, vers 5 jours, bien là, c'est plus le même genre de système météo qui est en jeu. Et cette relation-là peut encore là être valable, mais on comprend que c'est plus le déplacement des systèmes météorologiques, comment ça va être impacté, comment la circulation atmosphérique va évoluer, qui va avoir un impact sur ces extrêmes-là automnaux ou printaniers. Donc, la relation de Clausius, c'est pour ça qu'on s'est borné à mai jusqu'à septembre, je crois, parce que c'est dans cette période-là où ce genre d'événement-là survient, et c'est associé aux événements de plus courte durée, donc au maximum annuel de plus courte durée. Ceci étant dit, les changements climatiques vont impacter les événements de plus longue durée, mais les mécanismes en jeu sont différents.
C'est ça.
Merci beaucoup. Merci à tout le monde pour vos questions et vos réponses. Merci beaucoup, Alexis. Ce n'est pas quelque chose qui est simple à présenter et à faire non plus. Puis je trouve que c'était une excellente présentation. Fait que merci encore.